time to learn. Oh, there you are, friends. So we've seen what a qubit is in terms of a new type of information that's different from classical information. So classical information is specified in terms of bits, and we usually say that the state of each bit is either 0 or 1 or any other set of binary possibilities. The state of a qubit is a particular two-dimensional complex vector. We've shown how we write those down in terms of Dirac notation and how we change those states in terms of unitary matrices. Now, the final question is, once we've done that, we've done a quantum computation, we've taken a qubit, it's in a particular state, we've applied some quantum logic operations to it, and it ends up in a new state. What state is it? How do we look at the qubit? And there's some constraints now that quantum physics imposes on us. So if I have a qubit, it's in the state alpha 0 plus beta 1, and I want to look at it. So now I'm going to look. In physics, this is called measurement. What happens is that I only ever see 0 or 1. Okay? I never see a vector which is in one of these superposition states that we talked about last time. This going from an arbitrary state, any state where alpha and beta can be any complex number, to 0 or 1 is clearly not reversible. So once I've seen 0, I have no idea what the original state was. And this definitely doesn't happen completely randomly. It somehow has to depend on what the original state was. Otherwise, we have a kind of useless theory. And we know it's not useless because we found many uses for quantum physics. And one of the first things that was kind of figured out was the rule for the probability for which you see each of these distinct values. So I see 0 with a particular probability that depends on the initial state. So if I want to look at the probability with which I see 0 given the state was originally psi, and I've left exactly what psi is in terms of alpha and beta implicit, that is the coefficient in front of the 0 computational basis state modulus squared. Okay, so I take the square modulus of the complex number in front of the basis vector. And similarly, and now you can see why, by the way, since probabilities of this mutually exclusive and exhaustive set of outcomes has to sum to 1, why we consider unit vectors. So if you remember, at the outset we said, let's consider two-dimensional complex vectors. Maybe there's that sounds like a fun way to do computation. What does that buy us? I also specified that they would be unit vectors without really justifying it. That is obviously a constraint coming from quantum physics, but the reasoning is quite simple, not completely arbitrary. It is simply that the probabilities for the outcomes when I go to look at what the state is must sum to 1. Now if I have a computation, and we'll see this over and over, they always start in 1, with very few exceptions. Then something happens to them that's specified in terms of one of these unitary gates. And then the looking or the measurement is usually drawn as some unique sort of box. So this specifies a full quantum computation that can be done on a real device. Because by hand, of course, I can calculate the state vector and look at all of the components in some basis and update all of those components as I multiply these matrices. But in a real physical device, I have to consider a model where this look kind of constraint is being imposed. So a computational model which consists of taking two-dimensional complex vectors, applying unitary matrices to them, ending up with two-dimensional complex vectors that I can just look at, is not a computational model which I can realize in the real world. Because in the real world, quantum physics imposes this constraint, which is the result of looking at the qubit is not the particular state that it's in, but one of these two distinct possibilities with this probabilistic rule. And this rule has a name named after the person who first wrote it down, called the Born rule. All right, so if I want to analyze this computation, what I do is at any point where I don't know what the state is, I say here, I write down what the state is, and then because the circuit has some explicit notion of time as we move from left to right, then I can step by step through the algorithm. I mean, this one only has one unitary gate, but if there were more, then I would do this step by step. I can say that the state at this particular point in time is the unitary applied to the state of the qubit immediately before it. Okay. And then when I finally get to the end, I don't write down states anymore, because now this look operation, this measurement is being performed, and I have a distinct set of possibilities. It's either 0 or 1, and according to this rule, there's some probabilities for that to happen. And the first one is the coefficient of in front of the 0 of this vector down here. How is that specified? And modulus squared, remember? So I'll write down the modulus squared now. So it's the coefficient in front of the 0 vector. And down here, it's the coefficient in front of the 1 vector. Okay, so that's how you analyze a quantum circuit in its full glory. We'll always start in the 0 state, then we'll apply some of these unitary gates. After each gate, I update the state of the qubit to some new state. I can do that calculation by hand by applying the unitary to the state of the qubit immediately preceding it. And I step all the way till I get to the end. When there's a measurement, the measurement reveals a distinct set of possibilities with probabilities given by this Born rule. In some algorithms or information protocols, I may want to know what happens after I look at it. And what happens after I look at it is called collapse, and that sounds kind of extreme and violent, and in some sense it is, because after measurement, the state of the qubit is the observed one. So if I have any state whatsoever, so I have a qubit, it's in any state psi, I perform this measurement, or I look at it, or I want to read my quantum information, I get either 0 or 1, and the state of the qubit after performing that measurement is the one that I observed. So if I observe this 0 state as the answer, then the state of the qubit is 0 afterward. And that is a very discontinuous and, as we mentioned earlier, irreversible operation. So it has this terminology collapse, which is what I'm going to do.